Good, we are ready for the final presentation in this slot, which will give an overview of techniques used by major banking Trojans in the wild in a presentation called Browser Attack Points Still Abused by Banking Trojans, given by Peter Kálnai of ESET. Peter.
Men in the browser attacks are known for ages and widely understood. Is there anything new? Are there any updates in this field? Let us take a look. Hello, welcome to this presentation. My name is Peter. This research was done together with my colleague Michal Poslušný. We are both based in ESET, Czech Republic. The outline of our talk is as follows. We start with a brief recap of men in the browser attacks, briefly MITBs. Those are basically web injects and form grabbing techniques. Then, actually, the icon here, the Chromium, is chosen intentionally because mostly Chromium-based projects cause the malware authors the greatest troubles in implementing MITBs for browsers. Next, we provide a catalog of banking Trojans together with their approaches to MITBs, mostly against Chrome. And finally, we try to do something useful. We transform the results of this research into a plugin for Volatility framework that would detect these modifications, MITB modifications in memory dumps. This could help forensic analysts or incident handlers to quickly get some ideas about their cases. So, let us start with the first part. Web browsers are not able to defend against attacks by their own means. Let us ask a question. Which browsers do we generally use? Default ones, like Microsoft Edge, Internet Explorer, Mozilla Firefox, and then Chromium-based projects like Opera and Chrome as number one in the market. Let us briefly recap some timeline related to MITB's very first proof of concept, 2005. I wasn't in the industry those ages, but perhaps you recollect this. In 2007, the attacks got their name. And it was the same year the infamous career of Z-bot started, and it's still ongoing. In 2010, the very first MITB attack against Firefox was recorded, and actually, that implementation from that time still works nowadays because attack points for Firefox are exported and easily located for the attackers. 1 year later, also Chrome got its moment of attention. So first MITB against Chrome. However, implementations from those times do not work nowadays. One of the reasons, in 2015, Chromium-based projects have switched from NSS3 implementation of SSL functions to boring SSL, and the attackers had to re-implement MITBs. One note, in 2015, HTTP2 protocol was introduced. Malware authors do not love this protocol much because headers and contents are compressed and hard to parse for them. So basically, they just try to disable those. Let us peek into underground markets. This is an example of an advertisement of App Society project from the dark web. It's from October 2016, and it promotes usual stuff like PE injection, UAC escalation. However, it is proud of itself that it is able to turn off advanced network protocols. And it asks $250 per binary, 10 times more for the builder. The real world example of a builder is in the upper right corner. And down the builder, it's a detailed description of MITB support. Actually, the bot does not support Microsoft Edge. It does not support 64-bit Chrome. These are very prevalent software, so the bot is not very successful. So briefly, what are the attackers' goals? They try to locate browser's process memory, then they try to inject the payload, basically banking module, like the whole banking module, and then they try to find the attack points, which is complicated only for Chromium-based projects. And basically, they try to find a special virtual method table containing SSL functions of interest, and we shortly refer to this table as SSL VMT in the SQL. And finally, they install hooks, mostly inline ones, that would connect the hook with the injected module. Okay, the attack points, these Windows API are of interest, and for both, as well, Internet Explorer as well, Microsoft Edge. On the picture you can see Internet Options menu with the checkbox how to enable, disable HTTP2, just for the record. And we ask ourselves a question, if it's hard to inject code from some process to Microsoft Edge. We had some idea that Microsoft Edge should have some restrictions in this kind of things, so we wrote our own tool, own PE injector, PE loader, that that injected into Microsoft Edge, hooked the attack points, and leaked data from login page at myeset.com. So the conclusion is that MITBs, from the MITB perspective, like Internet Explorer equals Microsoft Edge. Even though Microsoft Edge has advanced mitigation policies like CFguard, and you can't load unsigned library within the process and some others, but these are meant to be against the exploitation of the browser itself, not against remote code injection. Attack points for Firefox. If you see those strings down below in the binary you analyze, you are probably facing a new banking bot that tries to disable H2 for Firefox by changing these browser settings. And this is the SSL VMT table with 3 highlighted functions of interest. These are the functions the attackers are after. And let's see in the SQL how they do it. Let's move to the second part. Gangs behind banking bots are persistent in their implementations of MITBs. So we demonstrate this on a few examples and one non-example. So start with that one. It's early version of Pepress from 2013, and this code is injected in browsers. And basically it just checks which browser it is, and if it's Chrome, then it will perform an infinite loop with 2 actions, like sleep 1 second and close WinSocket. So basically no internet running in a browser in Chrome if this code is injected. So after a few failed attempts, a frustrated user would very likely switch to a default browser and try it there. And these attackers had implemented their MITBs well for those at that time. Of course, this might work, but you couldn't sell this kind of code for $3,000, could you? Dridex gang, our predecessor, Magal Bas from IBM Trusteer, mentioned that the gang is really like sophisticated with focus on injections. However, they neglected their approach to MITBs, I would say. Because we were a little disappointed with their approach. Was not that robust. For early version of Chrome's, they just wanted to find a static pointer in text section of Chrome DLL. With a search based on patterns. And these patterns, they are on the left frame of the picture. And these patterns did not last more than 1 major build of Chrome. So they needed to be persistent. And on the right side, you see they check version of Chrome. Actually, from versions 54 to 60, there was very good method how to find SSL VMT by the SSL version constants. We will see later, I will mention later. So we ask ourselves a question, how persistent these guys were. And this is a table with rows. In 1 row, there is a Dridex version together with PE timestamp. And that was the first version that was able successfully attack the corresponding stable Chrome release. So we see that if you compare the dates, it's usually the difference only 2, 3, few days, perhaps with 1 or 2 exceptions when it was 2 or more weeks, but it could be because that we didn't catch binaries in the distribution, or the attackers went on vacation or something. Third example, spy Earthsniff, and these guys like impressed us with their approach. They were no pattern-based approach. These guys invited something new. We would call it instrumentation of the browser process. And in the first phase, they would like choose a large portion of a virtual method from relocation table and like hook them all with one single callback. And we can see in orange, those are hooked functions. Actually, this is SSLVMT, but in orange, there would be a lot of more virtual methods in data section of Chrome DLL. However, we focus on this one. So there are a lot of hooks, and there is a callback in red, checking if the buffer insert parameter contains strings like put, post, get. And if it does, then it will be SSL write function. And they would calculate the other two relatively. So very, very like robust method. And not to do this nasty trick with every browser startup, they would just save checksum of Chrome DLL and the relative offset of SSL VMT into the registry. So they would need to do this just with Chrome updates. And this is the final picture, those 3 hooked replacements of attack points in the SSL VMT table. Security researchers love to mock malware authors, and if we wanted to do that, this would be the case. It's a fork of spy Earthsniff. We call it also St. Nicholas case because PDB string contains this day of the year, and it also contains modification source code, so this suggests where the code comes from. But as we mentioned already in 2015, it was a switch from NSS3 to boring SSL, so the leaked source code of spy Earthsniff didn't work for recent Chrome versions. So they needed to re-implement MITBs for Chrome. And actually they invented some very loose conditions. That was fine because it worked. However, they were losing support for new Chrome very easily. And actually these were the only guys that were able to lose support, MITB support for Chrome within architectures like supporting 32-bit and not supporting 64-bit variant. No, all the others were not failing in this. And this is the reason. On the left, the code is good. It is just checking which browser it is. And if it's Chrome, then it's a sequence of procedures. And why would you like start to check your loose conditions on legacy versions? Like you have new Chrome release, and you start to apply loose conditions on these old versions, and the procedure would succeed, right? In the very late cases, and the return would be a false alarm, like not SSL VMT table, but some random function table in data section. So these guys didn't really persuade us that they were really aware of what they had been doing. The thing about Qbot is that the approach is completely different. Like, these guys were not after SSL VMT. These guys hooked, using inline hooks, some wrappers of functions of interest from SSL VMT. So it was complicated. There's an example of a pattern that would locate some attack point in some place in Chrome DLL, not in SSL VMT. So a complication to detect these hooks. And finally, a story around TinyUkbot. Like it was done by an 18-year-old guy from France, Augustine, and at first he shared his project with his contacts, I guess not friends, but some underground guys. And these guys, surprisingly, tried to profit off it on the black market, and the project was not successful there. But Augustine also got sad by this approach of his contacts, so he released the sources on GitHub, registered under email that was connected to a server belonging to his father, so many links for investigators. His father told the media, I'm very worried for him because some technology company told him they wanted to fly him to the US for a job interview as a result of posting that online. I guess not a job interview, but perhaps an indictment or two by the FBI. And perhaps he just wanted to join guys like Kevin Paulsen, Kevin Mitnick, and unfortunately also Whitehead, Marcus Hutchins, but at the moment we presume his innocence, of course. And one worried fact about TinyUkBot is that the crucial part of MITB implementation comes from a project officially supported by Google. It's called Web Page Test. It has its own manual by O'Reilly's. And this actually is the code shared by both TinyUkBot and Web Page Test. So on one thing, we are glad that Chrome caused struggles to malware authors to implement MITBs against it. However, on the other hand, Google is revealing crucial ingredients how to implement MITBs against Chrome, so what to say? So summary of hooking types, actually saw 3 of those. Replacement of a function in SSLVMT, inline hook in SSLVMT, and some custom method, which was done by Qbot. And this is a summary of targets. Firefox and Internet Explorer are a piece of cake for everybody. However, Dridex did not even implement MITBs against Microsoft Edge. So if you found a binary of Dridex that would have this implemented, it would worth a tweet, I guess. And perhaps we omitted some of your favorite banking Trojans. We tried to cover as many as possible, but this zoo is too large, so perhaps later. Okay, some brief remarks. Malware authors do not copy from each other. Definitely not. Banking modules, what is bad? That banking modules are not usually part of a binary in distribution. So you have to dig deeper, try to connect to CNC to acquire it. So we were really glad when we got banking modules. SSL version constants, that good signs for SSLVMT lookup were dropped in Chromium 61. So they have been dropped in Chrome 61 already for a month. And we didn't see, this of course affects many of those implementations. PyRSNF is perhaps all right, but Dridex and the friends really had to re-implement MITBs, the lookup for SSLVMT. Versioning is a very good thing because an incremental variant of the bot would suggest there may be something new, that it's worth to check it. And finally, support for browsers is a good indicator if the family is still active. So, because there are many bots in distribution that would not be able to attack recent browsers, but if support for browsers work, then the family is definitely active. And let us move to the final part. So, our browser hooks plugin. It's for Volatility framework. It extends API hooks plugin, which is a part of Volatility. It basically detects various types of hooks in exported functions only. So it's not the case of SSLVMT replacements over hooks. So we extended it with these three new hooking types. And what we added, moreover, if you have a memory dump from 64-bit system, 64-bit Windows, and you have hooks in 32-bit module, the original API hooks would not detect that. So we dig deeper and try to add support and succeeded in adding support for 32-bit hooks in 64-bit processes. Systems, sorry. And finally, we integrated these results from this plugin to Volatility graphic user interface, our favorite one. And if you are interested, I can show you a picture later. I didn't put it in these slides. And the release of this plugin is like today. We're releasing it now. I guess it's on ESET GitHub available. So any forensic engineer interested in this may contact us or download it from there. However, we also found some limitations, like some parts of Chrome DLL were paged to disk and not available in memory dumps occasionally. So this is a limitation, of course. And so, web browsers are not able to defend themselves against MITB attacks. And like gangs behind banking bots are really persistent in their efforts to implement MITBs. And if you see non-empty output of plugin like browser hooks, then it's a little bit too late. So what would be the conclusion? The conclusion is to use third-party tools that would protect browsers. Many AV vendors provide such tools. I'm not really sure how widespread these tools are, how many users uses these. ESET's solution is called Online Banking Payment Protection. And I guess this is the approach, protecting browser from the kernel, because the attackers usually do not visit this kernel space. So I guess I'm ready to answer any questions.
Okay, thank you, Peter. Any questions for Peter? Okay, if not, you mentioned that most of the browsers are attacked, except for that Edge in a few occasions was not being a victim of that attack.
Yes.
Is that perhaps because Edge has been written from scratch that it was not vulnerable against it?
No, definitely not. I guess it's just some reputation of the process itself that it's like somehow not reachable, but it's basically just the same method like Internet Explorer. I guess it's just guys didn't even try. They tried nothing, I guess.
Okay.
Yeah, and I guess if we had some time, this is the implementation for the graphic user interface for the output of the plugin. So we had like QBot infection, and QBot is like hooking Chrome DLL specifically, and there are some trampoline hooks in VS2 DLL, and you have also the hooking module base. Then you just right-click there, you store that hooking module, and then you have this output of DLL dump plugin. So you have the option to see some more details of this plugin, and there is also virus total search, and you can click up to the complete recognition of the threat, and the case closed in a few seconds, I guess.
Okay. No more questions for Peter? Oh, there's one here.
Do you think that browsers should like protect themselves from injects, or that it's impossible anyway, so no point in doing that? So like obfuscate possible inject points, etc.
Not even default browsers from the operating system do that. They don't protect from remote code injection, and then don't protect. Actually, it's Windows APIs. They are regularly hooked. Security solutions do that. So not for these default browsers. For Chrome, I don't think there are any attempts to do that. They are even revealing how to find these functions, unexported ones. So.
But do you think they should like protect these inject points, or that there's no point in doing that?
I guess perhaps they thought about that, and they discovered that it would be too hard, or like many banking trojans, many different approaches, and we have third-party tools. I would be really glad if like AV vendors convince their users to use this stuff, because maybe even like isolated browsers protecting from kernel space, that is like nice thing.
Okay, Thomas.
Maybe one remark to that last question about browsers protecting themselves. Actually, the only ones that are doing that, as far as I know, is Firefox. But the attempt is kind of ridiculous because what they are doing is actually that they are somehow checking memory loads, that they are checking DLL loads, and if somebody calls load library, they have a whitelist of DLLs that they accept, which is obviously an effort that is really ridiculous. It actually blocks a lot of more or less benign software, but it doesn't block the good guys. And that is why I would argue that basically these attempts of protecting themselves, they are not worth anything.
Okay, if there are no more questions for Peter, then please join me in thanking him.